Hello and welcome back to Textile Build. Thanks so much for joining us today for our second live Textile Build training session. Similar to last time, for those of you joining us live, please note that there are several ways that you can ask questions and interact with the Textile Build team during this live session. You can use the link at the top of the screen, which I will enable in a second. You can also join our Slack channel. And here we go with the audience tools. So there is the link that you can use to access the question and answer page. You can join our Slack channel, and then there are two links with icons on the first page of the slides if you want to use that as well. I'm just going to change those up. Okay. Okay, so let's get started. So this is the basic structure that we're going to be following for today. By the end of the session, you should have a working IPFS-based distributed app running locally in a browser. That's about as far as we're going to get today, but it will provide the structure for future updates and enhancements as we move through the course and learn more about dApps and P2P interactions and things like that. So just so everybody knows, today and for most of the rest of the sessions in this series, it's going to be pretty much interactive or hands-on the whole way through. So make sure that you have your IPFS daemon running locally. And if you need to refer back to the slides from yesterday, you should still have the links available there. But just pop a question up there if I need to post them back into the Slack channel or on the Q&A thread. Just have your sort of copy-paste skills primed and ready to go, because there'll be lots of code snippets that you can copy and paste into your terminal to check out what's going on. Okay, so if you remember from last session, we had a diagram that looked a bit like this one, depicting the general process of moving from raw data to a cryptographic hash of that data to a content identifier that allowed us to reference that data or to act as a fingerprint for that data. That's not really quite the whole story. What's actually happening is a lot more complex under the hood, and even the next couple of slides keep things a little bit simple, but it'll give you an idea of what's really going on. What's really happening is that the content is chunked up into smaller parts, about 250 kilobytes each. And then each part is hashed, like before, to create a digest of that particular piece. And then a content ID is created for each chunk. And then these chunks are combined into a data structure for which a single base content identifier is computed. And then this data structure is a representation of that particular file on IPFS. And the data structure is basically something called a Merkle DAG, or a Merkle directed acyclic graph. And you can see how this is essentially a graph where we've got 3 links that are connected to a node on that graph. So there are lots of different videos and explanations and things from Merkle DAGs out there. I highly recommend watching this video. Again, Juan Bennett from Protocol Labs. He explains how IPFS uses Merkle DAGs as our core data structure for what he and the project call the interplanetary linked data structure, or IPLD, sorry. So watch that video on your own time. I highly recommend it. It's not particularly long, but it's very useful, and it gives you a good idea of some of the motivations behind using the IPLD data structure. Now, this idea of linked data, it's actually something that folks in the decentralized web community have been talking about for quite a while now. It's something Tim Berners-Lee has been working on for ages, and even his new company, Solid, is actually building a business around that idea. So, and I highly recommend checking out their website, and they're actually presenting some of that stuff this week at the DWeb Summit. But essentially what we're talking about is a structure that models everything as a series of linked objects. So in this IPLD world, we have objects, and each of those objects basically have a data and a links field, where data is a small blob of unstructured arbitrary binary data, less than 256K, and links are just simply links to other IPFS objects. Right? So, and then those links themselves have a name, a hash, or a CID of the linked object, and then the size of the linked object. And this just represents the size, and it's really just so that we can have an estimate of object or file sizes without having to go and prefetch too much extra data. So it's very nice to have when traversing IPLD graphs and things like that. So we can kind of start right away by playing around with various objects from within IPFS. So we can do that from the command line, and we can take a quick look at the object structure of our cat image from our previous session. So here's a chance for you to do some copy pasting. So if you jump over to your terminal and you copy and paste that first line in there, and we run that, what you get is this sort of JSON looking structure where we've got links, and that's a list of links here, and then a data entry with some binary data, and the link has a name, in this case cat.jpg, the hash for that file or object, and then its size. And this is a relatively large one because it's a whole image of a cat. Now, if we want, we can actually take that hash and we can look at the IPLD structure for that particular hash. So if we do that, we have the same thing, links. In this case, we've actually got two sublinks, each without a name or with a blank name, and a hash associated with those values. And then they've got actual data chunks in here as well with sizes. And we can track those hashes all the way down until we get down to the bottom of that sort of hierarchical tree. Okay, so that's kind of fun, and we can start to play around with that a little bit. Chances are you're not really going to interact with IPFS in that way per se, but it gives you an idea of sort of what the underlying structure of some of these CID links look like. Now, the flexible nature of directed acyclic graphs, or DAGs, which we're going to talk about in a little bit more detail in a second here, let us represent just about any particular data structure that we want using IPLD. So, for instance, let's say we had the following directory, or the directory structure shown here. It's amazingly easy to add this directory structure to IPFS. And we'll actually use this functionality later on to publish entire websites by simply doing a recursive add like we have at the bottom of the screen here. So if we had that directory structure and we added it to IPFS using IPFS add recursively the test directory, we would have that and all of the subfiles on there. And essentially what IPFS is doing is it's actually creating one of these DAGs for us. And then it's returning the hash or CID for that top directory structure. So let's kind of look at an example to give you a bit of a better intuition for this. Okay, so assume that we've got this directory structure and all three blue files here, so hello.txt, myfile.txt, and testing.txt, all contain the same text, which is the classic hello world exclamation mark with a trailing new line. Okay, so when we do this and we add it to IPFS, we end up with a DAG structure that looks something like this, okay? Where, and this will depend on the actual contents of the files in your directory, obviously, you'll end up with a series of objects linked by their CIDs. So their CIDs will be the normal length IPFS CIDs, and they will be a hash representation of the underlying content. So what we end up with at the top level there is we have the actual folder without a name, but with a CID of, in this case, it ends with BWD. From there, we have direct links. So these would be IPLD links to big file, the underlying MIDR hello.txt and hello.txt file. And then from MIDR in the middle there, we actually have links to myfile.txt and testing.txt, both of which actually reference the same CID. In fact, hello.txt, myfile.txt, and testing.txt all reference the same content ID. And we have it represented twice here just to make things a little less cluttered. But this is a pretty cool idea because as we are referencing the content of the files or objects themselves, we get this level of deduplication here for free, essentially. So we've automatically deduplicated these 3 files in our directory structure and just created one reference for them that can be shared or accessed over IPFS. Okay, lastly, on the bottom left, we actually have our big file, which has been chunked into 3 smaller pieces, each of which has its own CID, which together form the larger file. And now if you follow all of these CIDs up the tree to the top, you get a CID that describes all of the contents below it. Now this is actually a critical concept for IPLD and IPFS. So here's our first Merkle DAG aside, where we're going to just give a little bit more details about how this whole thing works. So the fact that we have data and links gives our collection of IPFS objects a graph-like structure, as we've seen, or a tree sort of more visually. And again, just a reminder, DAG means directed acyclic graph. So these links are all directed. Goes from the top and points to sub-objects. The name Merkle actually comes from the name of the inventor, Ralph Merkle, and he actually patented trees of hashes in about 1979. But luckily, people use them all the time, and it's a pretty common data structure, very well known. Anyway, what a Merkle DAG gets us is content addressing, so that all the content is uniquely identified by its hash, which is a feature of a Merkle tree or Merkle DAG, including links to things that it references, which make up the structure of the object. So this makes a Merkle DAG essentially tamper-proof because all the content ends up being verified with its hash. And because we've got this hierarchical structure, anything above that object its CID or its hash will change if the underlying data changes. So if we have the right hash, we know we have the right content. Again, we're hashing the content, so we have no duplication. We can just repeat the same hash or CID instead of duplicating data anywhere. And because in the Merkle DAG world, all objects that hold the same content are equal, we get this deduplication. So we only store things once, which is very nice. So we've got this pretty powerful, tamper-proof, essentially efficient data structure that we can use to represent linked data. And we can play around with this idea of Merkle DAGs and chunking up large objects ourselves from the command line if we want. And so you can see kind of what IPFS is doing when it's chunking up these files and creating a DAG for you automatically. So what we can do is we can actually just grab a nice big JPEG to play with. And then you can IPFS cat it, or you can just download it directly using the links here from GitHub. Then you can add it locally. And if you catted it, you can make sure that the hashes match if you then go ahead and add it. So I'm going to just go through a couple of these steps so that you can kind of see what's going on if you're unable to follow along at home. So if we just do IPFS cat, and that is the CID for a large image. and I'll leave it up to you to access and view what the image is. It's nothing. It's all safe for work, so don't worry about that. So if we do that, essentially what we're doing is grabbing and assigning a file tree in cosmos.jpg to the contents of that CID. And then what I can do is I can actually add that locally. I don't need to, but for the purposes of demonstration, I will. So if I do that, you see right away that I get the exact same hash back. Phew, the IPFS works. Now what we can do is we can actually use IPFS ls verbose to take a look at the sub-objects of that particular CID. And so we get a list of hashes. In this case, there are 4 of them, and their size. In this case, and in most cases, they're all about 256K, except the last one, which is just picking up the leftover data. Okay. And if we wanted to kind of represent this visually, we would get something that looks a little bit like this. Where at the top there, we have that hash that I originally went and catted or fetched, and then the 4 sub-CIDs or sub-objects right here. So here's another awesome thing about using DAGs or IPLD to represent data on IPFS, especially when working with large files. Because to reference one single large data file, all you need is that base CID. And then you actually have a verified reference to the whole object, all of its sub-objects. So for large, particularly popular files stored, if a lot of peers are seeding or pinning that file, if you can just send around a CID of that base file and then request bits of the object from multiple peers. So this makes file sharing of large data quite simple. So the idea here is you really just need to reference, you just need the top CID to reference the whole object. And we'll actually end up playing around with this idea a little bit later on when we start to add code and things like that to our DApp that we'll get started this morning. And actually, some of you may have seen what this kind of looks like if you played around with the IP or the XKCD archive that was hosted up on IPFS. And by the way, for those of you who participated in our little homework, thank you very much. I'm trying to respond to everybody, and a couple of you sent in your responses this morning, so I will get back to you as soon as we're done here. Some very interesting and fun choices for XKCD comics. Okay, so we'll just do a quick DAG recap here. Merkle DAGs are a core concept of IPFS, and they're actually a core concept in a lot of other technologies like Git, Bitcoin, DAT. These DAGs are basically all just hash trees that are made up of content blocks, where each content block has a unique hash. And so you can actually reference any block within the tree, which means you can actually build up a tree from any combination of subblocks. So you can share sub pieces of a particular directory structure, for instance, subdirectories and things like that. But in reality, we're rarely going to actually interact with the DAG or objects directly. Most of the time, your friendly IPFS add command will create the Merkle DAG from the data in the files that you specify. We'll create the underlying IPNS objects for you and add them to IPFS. We've already seen how this works, so you don't really need to interact with this directly too much. But it's very useful to know what's going on. And so you can use this slide as a sort of recap or summary of what's going on. And there's lots of different ways that you can interact with it should you want to. So we can look at the references of our particular tree and Cosmos object. But we can also do a couple of fun things, like, I haven't actually added this to the slide, so you might not be able to see what's going on. But what I can actually do is take all of the subhashes of the particular object, and I can cat them all together to put together the image from those sub-objects. So what I'm doing is actually grabbing all of those sub-hashes. I'm using the trailing backslash here just to extend my single command onto multiple lines. And then I can actually assign it to a new JPEG object, in this case cat-tree-incosmos.jpg. And what that will do, if you want to run these lines yourself, is it will actually basically put that tree and cosmos JPEG data or JPEG image together from all of the sub objects. So there's lots of kind of neat ways that we can play around with how data is stored on IPFS. And essentially, IPFS is when you cat a single base CID, it's doing this for you. Now you can also, this is actually a fun tool that was just released very recently. You can actually explore an IPLD object in the browser at explore.ipld.io. And so what you can do is stick a CID in there that you want to play around with. And in this case, I've actually clicked on, there's a Git example up there that's actually quite fun to play with. And you can actually go and explore the structure, and it'll show you the various different paths that you can follow. This is a Git example, so we've got parents 1 and 2 of merges and things like that. And it shows you what the object data contains, how many links to that particular CID, what the multi-hash looks like. It's a great way to kind of explore and get a feel for how others have structured data on IPLD. So I highly recommend you play around with it. You can explore Git, you can explore Ethereum, you can explore IPFS, and all sorts of other linked data structures like that. So check it out, explore.ipld.io. In fact, you might want to use it for the assignment that we come up with at the end of the session here. Okay, so moving on, but before I do that, I'm just going to take a quick look to see if we've got any questions in the queue that need answering. Looks like nothing in the Q&A session, and just check the Slack channel really quick. In our Slack channel, I've posted the link to the presentation here. So if you want to, actually what I'll do is I'll pin it right now. And you should be able to access the slides from there. I've also posted a link to the video, but saying that now, I realize that you wouldn't know that I've done that if you weren't already watching the video. Okay, so back to our task at hand. One of the key pieces of the IPLD data structure is its hierarchical nature. And the base CID actually gives us a content reference for everything below it, as we've mentioned. And this core feature is essentially what gives us an immutable linked data structure. So a data structure that can't be edited. So because nobody can change the content of an IPFS object without the address of that object also changing, then by changing anything below the base CID, the base object, the base CID, we therefore must also change the CID of the base. So this is a pretty big idea. And the idea of an immutable, or sometimes you hear like a permanent web, does sound a little bit scary. But it's really more of a misnomer, I think. What we're really talking about is an immutable web, not necessarily a permanent web. Because on an immutable web, content can still disappear if nobody ends up hosting it. So it's not so much permanent as it is an immutable web. So I'm going to stick with immutable rather than permanent when I talk about these things because it makes more sense. Although a permanent web certainly sounds a lot more newsworthy. Anyway, what we end up with is a fairly useful concept that gives us a couple of nice things, right? We get deduplication of data, which we've already talked about. We get content verification because we know that if it gets modified, its CID will change. So if we get something with the wrong CID, we know we're getting a different data source than we requested. This makes it pretty hard for anyone to add malicious code on the way to a particular data object that I'm requesting on its way to my peer. long and the short is content added to IPFS can't be changed. Okay, but this is all well and good, and many would argue it's actually a fundamental to a decentralized web, but it's not very practical if we're talking about dynamic content. So what about things that change, like websites or blogs or social media feeds, and pretty much all of the services that we enjoy on the current Web 2.0? So for that, we have something called IPNS, or the Interplanetary Name System. So what IPNS lets us do is basically just add immutable content, things that can't change, but then we update a pointer to that content so that as the underlying content changes, but the way we link to it stays the same, right? It's basically like adding a little bit of immutability or mutability to a permanent immutable web. It's essentially like a self-certifying file system. So it maintains some of the niceties of content verification. So you know you can trust the IPNS link because you can verify that I or whoever is supposed to be the one who published it from my particular peer ID using my public key or private key. But it adds the niceness of mutable references so that we can actually update things as we go along. So this way I can update my website without having to have everyone change their CID for it to access it, which is quite nice. And we'll talk a little bit more about peer IDs and public and private keys in a second. So I've been, this IPNS or Interplanetary Name System, essentially it's a global namespace that uses public key infrastructure to essentially build up trust chains for publishing content. So, and a trust chain is basically a chain of cryptographic keys so that we can essentially trace back the provenance of a particular key. And that's a sort of very simple way to explain it. But what this gives us is both encryption and authentication. And it's also, IPNS itself, compatible with other name services. So we can map things like DNS entries or onion addresses or bit addresses to IPNS addresses. And this makes it possible to trace through a DAG for IPNS and link it to different websites and link it to different objects on the regular web. There are already a lot of examples out there, some that are actually linked at the end of this slide, to play around with IPLD or IPNS. So it does work already and people are using it. Having said that, IPNS, like a lot of decentralized web technology at the moment, is still a work in progress. In fact, you should really be treating all IPFS at this stage, all IPFS related software and tools as sort of beta quality, or at least beta level software. Anyway, IPNS is still pretty slow. And in fact, not all IPFS implementations, so we'll find out later today, including the JavaScript version, support it yet. Although there is actually a PR out there right now that should make it available in the JavaScript implementation in the next release. But it is usable in several contexts. So we're going to start with something simple right now using IPNS, and then we'll use it in our basic DApp or decentralized app example in a little bit. So say I wanted to share information about myself with various, preferably decentralized web services. But I want full control of this information so that I know and have a say in what information I'm sharing with these services, unlike standard services that sort of do a lot of tracking and things like that. And then I want to be able to decide what I do and do not want these various services to know about me. Okay, so to share this information programmatically, maybe if I was a developer, I'd create some sort of simple RESTful API for services to access. right? Or maybe I'm a service that provides a way for people to share information about them. So I'd probably include things like name, birthday, social media links, work information, etc. And then I'd probably serve it up as a JSON structure or something like that. So I can actually already do this quite easily using IPFS as the sort of backbone for that. And I can just add a JSON doc with the right information from my peer, and then I could even view it online. And I could call that sort of done. And so here's a couple of commands here. I'm just using Vim to edit a JSON file, which I'm just calling JSON with no file extension. And in there, you could stick all sorts of information. And so it might look something kind of like this, where I've got name, first, last, and other. I've got a bit of a bio about myself, my date of birth, some social media links like my GitHub, and et cetera, et cetera. Down lower, I might include work information and things that I'm willing to share with a sort of online profile or something like that. And then what I can do is I could then add this file to IPFS. And in this case, I've got a little bit of a long string of code here. And it could actually be shortened a little bit to something a little bit simpler. But what we're going to do is actually add this JSON file and wrap it in a directory, and then just grab the hash that gets returned from that output. Then what I can do is I can access that particular file over IPFS, right? And if I do that, I get something sort of like this, right? So we've got an actual JSON file that's being displayed over on the web. And in this case, I'm just accessing it using my local IPFS daemon here. So hence the sort of localhost IP address here. So if we do that, we get something like that. That's pretty great. And in fact, we could say sort of job well done. I have created a very basic JSON API which people could access. But that wouldn't be very fun. It's pretty simple and not particularly useful yet. But what we're going to do is we're going to all do this, and then we're going to tweak it a little bit and make it a little bit more useful. So I really do mean it. Go ahead, if you have a second here, copy and paste this example that I have up on the screen here in the slides, and paste this into a new simple JSON file. Call it JSON with no file extension or anything. And then fill it in with some information about yourself that you are willing to share with the decentralized web. So we're going to be adding this to IPFS in plain text, not encrypted. So make sure that you aren't sharing any, particularly personal information or passwords or anything like that. So I've got this example template here, and we'll use it in an example later. So it would be great if you do this now. If you don't feel like it, or if you're not following along with code right now, we can use an example I've created, so no big deal there. But what you can do here is just bring up your favorite text editor, copy and paste the above text in, update it with your info, save it to a file called JSON, and then just run the last 2 lines of code on the previous slide to add and view the content on IPFS. So I'll give you a minute or two to do this while I check if there are any questions in the queue or in the Slack channel. So here's a quick question on the Slack channel here. The IPFS doc says that IPNS is only valid for 24 hours by default. What does that mean? What should I do if I want to keep it valid forever? Yeah, great question. That's true. There are multiple reasons for why IPNS publishing expires. Essentially, all you need to do is just republish it, right? So you can just run the command again. If you're hosting a website or something like that you want up there constantly, you can just create a cron job or a regularly running process that will just keep publishing that page for you. So it's pretty easy to handle. It's just an extra step that's required. And I won't go into why they expire here today, but we can talk about that later in the Slack channel if people are interested. You can, so the other question is, we cannot pin an IPNS hash, right? And the answer is actually you can, and it will pin the correct content. And yeah, so that's, you can do that. And then so that second part of that question kind of get answers there. All right, perfect. All right, so let's just jump back onto the slides here. All right, so it will be fun if you do create this, but we've got some examples if you want to go through it. You don't need to. So, okay, so say you did follow along and you created this object and you added it to IPFS, or you're just playing around with mine. Unfortunately, the immutability of this hash file doesn't really cut it for a dynamic API. For instance, say I create a new social media account, or my job changes, or my bio changes, or you know, whatever. So using IPNS, we can actually publish the hash to our peer ID, which obviously doesn't change, and then we can update the API response file as needed. So we can actually have a dynamic API essentially. Additionally, we have an API response that can be authenticated and linked directly to me, which is quite nice, right? This is a pretty cool idea, and it only requires one extra command to complete that. So I'll show you what that looks like here. Oh, here we go. Actually, I already have it up there. Right, so what we can do is we just use IPFS name publish to publish that new data. And in that situation, I've got $, squiggly brackets, hash, which is actually just referring back to this hash that we saved from the previous step. You could also just replace this with the hash itself if you wanted to copy paste it there. So now we can make changes. We can publish updates, and then we can update our IPNS hash, or our IPNS values. So in this particular case, we could make some changes. We could republish. The links don't change, but the content does. So again, you might edit the JSON file with your Vim editor. You might hash the file, and then you might publish it again. And so these are the commands that you can use to do that. You can also use different keys for different content. And actually, while you're at it, you can go ahead and make edits to your JSON file and update it and see how that works. But anyway, for added flexibility, you can use different keys for different content. So, and this is pretty easy to do. You just do IPFS key gen, and then the type default is RSA. Size should really be at least 2048, and then you give it a name. So I could publish my API using one key, my website using another key, and my Buffy the Vampire Slayer fanfiction using another key. And I could update these as I change my content, and there'll be no clashes or anything like that. So IPFS keygen, and then IPFS name publish, and you can just specify which key you want to publish to. And so I actually did that earlier, where I published some content on behalf of my dog, and we'll see an example of that in a little bit. So this is definitely a big improvement, because now we essentially have a dynamic API that we can update with new data as it comes. But these long hashes aren't exactly easy for humans to remember. Pretty much impossible, actually. And there are a lot of other solutions out there for trying to address the sort of non-human readability of hashes, including things like URL shorteners and other sort of naming schemes. These all require kind of hacks in order for that to happen, and in some cases, a centralized system that's tracking shortened URLs and things like that. So that's not ideal. But we do have to play around in the existing web technologies. So right now, one of the easiest solutions is actually to use a DNS TXT record on a domain name that you control. So something that just looks like this is a TXT record where you replace the hash with the actual IPNS hash. And if you're just publishing using your peer ID, then it'd just be your peer ID. And then we can access it quite nicely at a particular URL like the one at the bottom here. So it'll be just ipfs.io/IPNS/your domain name. And I'll show you some examples of this. And you don't need to have your own to run through the course today. I'll show you some examples. But if you're actually managing a site, you can use some of these things. So I actually have my personal site registered with GoDaddy. And so this is just a screenshot of me creating a TXT record with a DNS link to my IPNS peer ID hash there. And I'm creating it for an API subdomain so that you can do something like api.carsonfarmer.com/ and I'll have some content there. So in fact, I've created something like that already as an example. So when I visit https ipfs.io/IPNS/api.carsonfarmer.com/JSON, I'll get my JSON API response, which is pretty cool because now I've got this much more usable link to share around. It's a lot shorter. It doesn't contain a bunch of gobbledygook base 58 encoded string. But I still am, kind of playing around quite obviously in the IPNS or IPFS world. And so we can do better. It's still pretty messy, and if we want the average web user of today to access our decentralized content with minimal effort, we really don't want them to have to deal with gateways and IPNS and IPFS domains and things like that if they don't have to. And a major feeling of the decentralized web community is actually that the user experience really shouldn't change that much. The transition should be transparent, but it should be easy. That's how sort of decentralization technologies are going to win here. So we can create an A record on our domain, pointing to our subdomain, or pointing our subdomain to the IP address of an IPFS peer that's listening for HTTP requests on port 80 HTTP, so that we can route through there. And the IPFS public gateways you can do that with. If you've got your own gateway running, maybe you followed some of our earlier blog posts about getting an IPFS peer up and running. You can point to one of those API or IP addresses, and you can do it that way. But we can actually do even better than that, because we don't want to have to rely on IP addresses being static. In fact, that's one of the things that we don't like about a centralized web is these location-based addresses. So we can use a CNAME record to point at the DNS records for the particular gateway, so that if the IP addresses change, our CNAME records will still point to the right place. Unfortunately, in practice, CNAME records don't allow other records like TXT records. But the folks at IPFS have allowed us to create something called so you can create a DNS TXT record for _DNSLink.your.domain, whatever that happens to be, and it will still work. So IPFS and the gateways will essentially respect that DNS link if you do it this way. So what does that look like in practice? Well, again, if you're say hosting on GoDaddy, you can create a CNAME record where you've got that API subdomain pointing to gateway.ipfs.io or your own gateway. I actually have one at ipfs.carsonfarmer.com, which you could play around with if you want, but please be gentle. It does cost money to run. And then you create a TXT record where the host there is _DNSLink.api, and the TXT value is the DNS link, just like we had before. Okay? And so you can substitute your own things, but now what we have is a much nicer looking URL. A normal Web 2 URL pointing to a futuristic Web 3 resource hosted on the decentralized web. So this is pretty cool. So if you own your own domain or you manage one for your team or your employer, you now actually have a relatively easy way to implement a mostly static, sort of dynamic API in a decentralized system. So you can actually start running entire sites and APIs and things like that on the decentralized web, which is a pretty powerful thing to be able to do. Okay, so now that we have that stuff covered, I'm just going to take another quick look at to see if we have any live questions, and then we better get into our examples pretty quick here, or we're going to run out of time. And by and large, throughout the course, what we're really going to do most of the time is introduce examples, and then you can kind of play with those throughout the remaining days of the week or before the next session. So we'll probably get to that point today as well. So if there, I'm just going to check real quick for questions, and then we can keep moving on. And it looks like we're good, so I'll keep. Oh, we got Troy typing a question here. Okay, all right, I will keep going here. Okay, so back to content addressing. As I've mentioned a couple times before, key feature of the distributed web is accessing data by content. And this is pretty useful because we can actually access data efficiently from any peer that has the content we want. But this idea doesn't actually just stop with content. We can actually use cryptographic IDs for peers as well. And the reason we might want to do that is because a peer's location can actually also change over time. So this is sometimes called native roaming, or even hop between multiple devices, right? And this is called runtime freedom. So, you know, if we have some peer account and we've got it installed on multiple devices, we might want to take that into account. Now, tracking this would be pretty hard with traditional location-based addresses, like IP addresses, because they're linked to a particular server location. It also means things like mobile devices are pretty hard to set up as content providers. They're really only just consumers, at least in a decentralized way. Right? The way we do it now is you have some centralized server like Instagram. You've got a bunch of clients, your phones, they submit data to the server, and then that server provides the content to everybody else. But in the decentralized web of the future, we can actually have location agnostic peer networks, which at a very high level just requires peers to identify each other by some kind of peer ID, which is pretty obvious. So in the IPFS world, peer IDs are identities that are unique to each peer interacting on the IPFS network. And they're very similar to CIDs, right? So this is pretty nice because as CIDs can be used to authenticate content, peer IDs can be used to authenticate peers. And you might call these PIDs. CIDs and PIDs. So that way we know we're sending and receiving the right data from the right peer. In practice, IPFS uses a public key cryptographic system to do a lot of the work required to authenticate and encrypt data between peers. And in fact, when you initialize a new IPFS peer, a pair of keys are generated. And one is your public key, which you can share, and you can share with peers so that they know how to communicate with you. And one is your private key, which you need to keep private, obviously, which you can use to decrypt content that comes at you using your public key. So this is a pretty nice system, and IPFS uses the RSA crypto system to generate key pairs, which is pretty common. And it actually all starts right away. So when you actually initialize your peer at the beginning, you may recall from before when we did that, you got a bunch of text printed to the screen. And in the middle there, it says generating a 2048-bit RSA key pair, and then it prints off your peer identity. Well, this peer ID is essentially the multi-hash, hopefully you remember those from previous class, of your peer's public key. And so you can play around with that and take a look at it. And actually, we have a blog post on our blog that talks quite a bit about peer IDs and how that works. So I recommend that you check that out. But essentially what happens is you've got your peer ID, and when two peers connect to each other, they exchange peer IDs and public keys. And anytime two peers connect on IPFS, there are multiple checks to make sure that the peer IDs match the public keys that are being exchanged. If they do, then we know we're communicating with the right person. If they don't, we would just cut off communication. So it makes sort of man-in-the-middle attacks and things like that very difficult. I'm going to skip this slide, but it's up here just for fun. You can play around to see how you actually compute a peer ID on the command line. And if you have any questions, join us on our Slack channel for that. It may require you to install some Python tools. But peer IDs tell us who we're talking to, but not where those people are. So as the peer's IP address or whatever changes, that underlying address will change. That's no problem. But along the way, other peers can dynamically request the address for that peer. And you can do that using IPFS DHT find peer and the peer's ID. And then it'll give you back these things like this. These are called multi-addresses, and they are essentially just a special version of a network address. And so here's another quick aside here. These little beauties are designed to address some of the deficiencies with legacy addressing systems. So they model network addresses like URL paths or DNS addresses, and they sort of model these as arbitrary encapsulations of protocols. Essentially, it converts an address into what looks a lot like a file path. And it's useful because then we can support addresses for any networking protocol that might crop up throughout the IPFS system. So it doesn't matter where your device is located or how it can be found, we should be able to represent how to find it. It also works with the whole interplanetary file system in terms of looking like Unix file system paths. Okay, so what are you going to do with all this new information about peer IDs and networking addresses and things? Hopefully nothing for now. You shouldn't really need any of this low-level interaction to do anything on IPFS. But it's useful to know what's going on so that as you're designing APIs and you're designing dApps, you know how this underlying communication is going on. Okay, and here's a quick recap, which you can kind of read through on your own. The idea is basically that the centralized web is bad, the decentralized web is good, and IPFS will save us all. But seriously, we've actually covered quite a lot so far. We've covered how to install, add, pin, get, cat, and explore IPFS. We've covered what is IPFS, distributed hash tables, content IDs, multi-hashes, DAGs, lions and tigers, oh my. And we've kind of seen that all of these tools are designed to be essentially future-proof. We're designing a web that is going to grow, and the tools that we're building for it now should be able to grow with it. But enough with all that. Let's actually start to play around and build some code. So we're almost out of time. But what I want to do is just set you up so that you can actually get a dApp up and going in the browser, so that on Tuesday, when we start our session, we can actually start extending that tool or extending that dApp directly. So first things first, you should have already installed Node.js if you didn't have it already. And hopefully you've also already gone and cloned our dApp template. If not, you can copy and paste that into your terminal now, git clone, and I'm calling mine textile-dap, but you can call yours whatever you want. Just remember what you call it. And then you can just change directories into that default project. And then make sure that you can install the packages that are in there, yarn install, or if you prefer npm, you can use npm. And then make sure you can build it, yarn build, and you can use npm again there. So that's the first step. First things first is get the example dApp and make sure that you can build it. And if you have any questions or problems with that, don't hesitate to reach out on our audience tools thing or in the Slack channel. And then later on today at 6 p.m. Pacific time, we will have our office hours where that would probably be a good time for you to ask questions and troubleshoot issues that you have playing around with the dApp on your own. So once you've done that, the template itself is actually pretty simple, and we have fairly minimal dependencies in there. Most of the deb dependencies that are already in there are just for transpiling JavaScript to run in the browser. The only new runtime dependencies that we have are jQuery, something called query string, and window.ipfs is required. So the first two, jQuery and query string, are pretty standard web dev libraries, and I'm including them because chances are, if you've developed a web page before, you've used these. The third, window.ipfs is required, is obviously an IPFS specific library, and we'll see what we can use this for in a couple of slides. But for now, you can just add these packages to your project using yarn or npm. And then once that's done, you can go ahead and run yarn watch on the project. You might have to install yarn with brew, by the way, if you're on OS X, or apt-get it on Linux, or download a binary if you want on Windows. And essentially what yarn watch will do is it builds it and fires up a little web server with a watch process that will rebuild the project each time you edit a file. So we find this really handy for developing little projects like this, which is obviously why we included it in our template. Now, I'm not going to go over all the libraries that we've included in the template, but you can take a look at our blog post, which I have linked at the end of this slide deck, for some of the details there. In general, we're using Browserify to make our code run in the browser, and Babel to convert from ES6 to boring JS that browsers understand. But if you're able to yarn watch this, and again, reach out on the Slack channel or the audience Q&A thing if you have any issues there, you should be able to open a browser, and you hopefully will see something that looks like this. Right? Now make sure you're running it as localhost on port 8000, not 0000 on 8000 on port 8000. Make sure you're running it as localhost. And again, if you're not seeing something like this, make sure you reach out and ask a question, and we'll try to get you back on track. Okay. A couple more things before I sort of set you off playing around with your DApp for this week. A quick aside, you may have noticed on my previous slide the little IPFS icon with the number 790 above it. So that is actually the IPFS companion browser extension, and it's showing that my local peer is connected to 790 peers. So the IPFS companion is a browser extension that makes access to IPFS resources in your browser a little bit easier by basically running an IPFS peer in your browser, or accessing your local IPFS peer from your browser. But what's really nice about this browser extension is that it actually exposes an embedded IPFS node as window.ipfs on every web page that you access. This is super cool because it means that our DApp can detect if that exists, and then we can use it instead of having to create a one-off JS IPFS node in the browser. You don't need to use this to run IPFS-based dApps, but it does make them run a little bit better, because instead of firing up a brand new peer in the browser, which then has to go out and connect to all these peers and to be able to start routing content, it can use the one that's already running on your system, which means it's kind of already been bootstrapped up and ready to go. Now, for today's example, you're going to be interacting with IPNS hashes. And unfortunately, the JavaScript IPFS nodes don't support that on their own yet, as I mentioned earlier. But if you have the IPFS companion running and linked to your local peer, then it will work because it will be using your local node. So at least for this week, make sure that you are using the plugin. For now, it works on Firefox and Chrome, and it will make your development cycle a little bit nicer. In future examples, you can actually use window.ipfs-fallback to detect if window.ipfs exists, and then fall back to a version from a CDN if it isn't available. But for now, we'll use window.ipfs is required package, and what that'll do is detect if we have window.ipfs, and if we don't, it'll just display a download link for the IPFS companion browser extension. And I'll show you what that looks like in a second before I leave you for the morning. So you can go in, and once you've installed the extension, you can go in and edit your configuration using the little configuration button, and you can actually turn it on and off if you don't want to use it for a particular browsing session or whatever. But what you can do is you can go in there and just make sure that the gateway and the API ports match what you have running on your local system. And again, during office hours or right after this session, I'm very happy to answer any questions that people have about how they might want to configure that. Anyway, before I let you go, what you can do is you can open up your JavaScript console on your browser if you've got the DApp up and running. And you can check out the console. And hopefully you'll see something that looks like this, where we've got an entry in the console that says running go IPFS blah blah blah. Hopefully the version is the same as mine with ID blah blah blah. Hopefully you see something like this. Your ID is obviously going to be different. If you do see something like this, congratulations, you are actually running a decentralized app in the browser. And then the next step is to make it do something fun. Hopefully, if you've got the IPFS companion browser extension installed, that ID should actually match the ID of the one that you have running on your console locally. And in my case, it does, which is good. Anyway, so your assignment or your exercise for this week is essentially to make this a little social profile DApp inspired by about.me or some sort of website like that, where it's got a profile picture, a short bio, links to social media accounts, and some work information. And it actually draws on all of the information from the JSON API that we created earlier, so that's why we were doing that. So to ease your development on your own, you can check out the diff of this file with our original template app so that you can see what needs to be changed in order to make this happen. And there's a link on the slides, but you can also just go to the GitHub site for the DApp and check out the build profile demo, which is a separate branch to have the code handy to play around with and stuff like that. You can also, if you want, if you've git cloned the repo, the template DApp repo, you can actually check out the build/profile demo branch, which has all this code in it already. So you just have that code running locally. You can fire it up and test it out. But essentially what's going to happen is that you're going to fire up this thing. It's going to query your IPNS ID, and it's going to go out and fetch the JSON data that you've hopefully added to your IPNS key. And so there's a little bit of code here. We're pretty much over time now, so these slides here are for you to kind of go through and look at and see the different outputs that we have. And you can actually go through line by line, and it will kind of explain little bits and pieces here. And I'm happy to sit on the Slack channel if anybody has any questions about any of that stuff. So you can go through and see what all these different bits and bobs do. Here's the sort of main piece of the puzzle right here. And then what you should end up with is, if you don't have the IPFS companion running, you'll probably get something that looks like this with just a spinner that spins indefinitely. If you do have it installed, hopefully you'll end up with something like this, except it will contain all of your profile information. The other thing you can do, if that's not working, or if you didn't go ahead and add your own data to your own profile, what you could actually do is you could add a query to the query string for the URL. So up here at the top, $PID equals, and you can stick my dog Lucas's IPNS key right up there, and you will get his profile page. And so you can use that to play around with if you want, so that you can see what's going on there. So he's the head of marketing here at Textile, and you can play around with his profile. He's even got an Instagram account if you want to link the social link there as well. So you should just be able to copy and paste that from here, stick it up there as a PID, and you can use that to develop with. And as you refresh your page, as you make changes, it should go out and fetch Lucas's thing. And I'll make sure that I publish it every 24 hours so that you can continue to play with it. Okay, so that's all we have for today. We're pretty much over time. So hopefully we've kind of set you up so that you can play with this relatively simple DApp. It relies on several core components of IPFS. So the stuff that we discussed today, IPNS, and getting and fetching and catting files, that's all in the DApp. And these are things that the DApp relies on. Now, for this type of DApp to actually work, you need to make sure you actually publish the IPNS file, which is probably not all that realistic for your average user. And so we'll discuss in future classes how we might make that a little bit easier for users by providing some tools to edit content directly. But it does provide a nice example for how something like this might work. Notice there's no databases or interactions that way, but we will get there. And so next session, we'll start to build on this initial app. So make sure you keep any tweaks and improvements that you've made handy. And you might want to create your own fork of the DApp template, and you could push your changes up to that in whatever software management strategy you like to use. And then we'll build on this and we'll add some functionality as we go along, right? And so I'll assume that at least you've played around with each subsequent DApp at the end of the session. So try to make sure that you have in order to move along with the course. Okay, so that's it for now. If you want, you can do a little bit more with your DApp by adding a QR code or figuring out how to actually represent your JSON file as an IPLD DAG. And that would be a kind of fun experiment. It's a little bit of work, but you can do it because I did it earlier, and you can actually explore it and play around with it a little bit. And I have some hints for how you might do some of this stuff in the slides here. So please, do play around with that. IPLD is a very flexible data structure, so you can represent a lot of different data structures with it, including something like a JSON file. In fact, it's perfect for that sort of thing. And so if you click on this link here, there's actually a working example of, I added about half of the information from Lucas's profile as an IPLD object. And as always, there's a couple additional resources. IPFS for websites is pretty handy if you want to do that, if you want to put your own website up on IPFS. The slides from today largely came from a couple of different Textile blog posts that we've published. And then, as always, there's a couple useful IPFS sites that you should probably check out. So yes, hit us up on our Slack channel. You can make comments on the YouTube video. These will be moderated, but I'll try to get on those pretty quick. Otherwise, we'll see you next week, where we're going to dive into a little bit more detail and a little bit more time directly working on our DApp together. So until then, I'll see you next class.